So, today I will continue on the issue of robot sensors. Recall that we had covered this topic earlier, and we had looked at internal state sensors and external state sensors. In the internal state sensors, we had covered sensors which were necessary for the basic movement of the robot, whereas in the external state sensors, these sensors augmented the capability of the robot, and we saw a few of those external state sensors like touch sensor, tactile sensor, that is. And today what we are going to start out is what is called robot vision. Okay, robot vision is the most powerful sensor you can think of in terms of augmenting the capability of a robot. This is also of course called machine vision because it is not only used for robotics, it is also used for industrial vision applications, for inspection, for other tasks which are not using robots, but maybe some other automation tasks, or as assistance to a human operator giving useful information. Now, basically vision deals with issues of how you take images and how these images can give you information about the real world. So, it basically deals with images. And what is a image? Image is basically a reflection of the three-dimensional outside world onto a planar representation, right? And that is what we mean by a image, is that we take the outside world, we take a picture of it, and we have a two-dimensional representation of the three-dimensional world. If we take, basically image is at one instant the representation of the world. So, you can take images at intervals of time. So, you can have one image or multiple images, and from that image if you try to extract out information about the real world, then we will call that image processing. So, image, as I said, is basically a 2D representation or reflection of 3D real world. Okay, and we are interested in taking the image from image we want to extract useful information about the real world. Okay, so now if you look at image processing, there are some essential steps which are required, and these will generally be classified as low level tasks and medium level and high level tasks. So, in the low level task, if we say the first thing is image acquisition. Okay. So, well, this is one task. Let me enumerate all the tasks first, and then we will look at each of them in more detail. This is of course very clear. This is basically sensing of image. This is the sensing part. Next, once you have a image, then we will do some pre-processing. Now, pre-processing is usually used for reduction in noise, And noise, when we say, we are talking about picture noise, normally we associate noise with audio signal. This is in picture, if there are defects, then it could be due to some noise present in this thing. And of course, enhancement. Enhancement refers to the fact that if you have a picture which is generally dark, and there is information in the dark portion which will become very difficult to see. So sometimes we would like to transform the image so that we are not adding any information, we are not changing the image, we are only transforming image intensity levels so that the dark image starts to look brighter and features in the dark image become little more discernible. Once we have a proper image which we have done by pre-processing, then we come to what is called segmentation. Okay, segmentation basically refers to separating different regions. Regions of the image which hopefully are connected with the different objects which are present in the scene. Then we come to the next step, which is description. That is, each of the segment or the sub area or sub image that we have, what are the characteristic features that we need to look at so that we can distinguish different regions. Okay, we will describe a particular region by some properties. The property could be shape, could be size, could be general gray level or brightness or color, and so forth, so on and so forth. Then we come to the next step, which is recognition. And recognition is basically referring to the fact that you have different regions available in the image. The image we have already described in terms of different parts of the image, and then we are going to identify regions as region belonging to a particular part, for example, okay, or an object. And then finally you can say we have to interpret. So interpretation, basically we want to assign meaning to the scene that is in front of us. Okay, obviously some of these tasks are fairly well defined, some of them are not so well defined, or so we would say that the first one definitely is part of the low level task. Second one is also predominantly a low level task. Low level task is the task in which we don't have to we are not using that much of discerning, we are doing some things automatically. So image acquisition and pre-processing are going to be low level tasks. Interpretation is certainly a high level task, where we are trying to assign meaning to what we are seeing, or what are the different segments in the image and what does it mean. Is the part good, is it defective, or where do I hold it as far as the robot is concerned. All these are higher level tasks, and basically we will say that segmentation, description, part of recognition are lower level or medium level tasks. So let us start out by looking at the acquisition. Image acquisition, and for acquisition what do we use? We use a camera. So it will be a video camera. Traditionally we have used a technology called VDCon. Okay, let us look at how a VDCon camera works. This is the, if you have seen television studios, you will see some big cameras, and those cameras are typically VDCon cameras. So VDCon camera essentially consists of a picture tube with a face plate and you have a way of generating a stream of electrons. So, this is my source of electrons here. I will have some coils which are going to focus coil. This is the what I call face plate, and by applying suitably heating up this element, we can generate electrons which are going to be attracted towards the face plate. The path of the electron is basically governed by other coils. So, if I have some other coils here, this will be for deflection. So, electron E beam deflection. Okay. Now, there will be coils in the along the vertical direction as well as there will be coils along the horizontal direction. So, you will be able to scan the face plate by using these deflection coils. Now, the critical portion is in the near the face plate. At the back of the face plate, we have a transparent electrode. Transparent electrode. So, it is basically is a good conductor of electricity and it is transparent to light. So, whatever light is coming through the face plate gets across the this electrode. Next to the electrode, we have a deposition of photosensitive material. They are in the form of small globules. Okay. So, this I will call the photosensitive layer. Okay. These are photoresist material which when you have photons striking it, its resistance changes. Okay. Next to that, we have a fine grid of another electrode which is connected to positive charge. Okay, I am sorry, it is connected to negative charge. So, basically the idea is that we are going to slow down the electrons by using this grid, so that the electrons strike the back of this photosensitive layer with very low velocity. Okay. What we will do is this transparent electrode will be assigned a positive charge. So, we assign positive charge here. What happens is, supposing there is no light coming, this portion here is optics, which means your lens, etc., focusing lens will be there in the camera, and behind that is all this stuff here. So, when there is no light coming at all, then this positive charge will be distributed. There is a good conductor here, so you will have positive charge existing here, and we are depositing negative charge here. So, negative charge will be existing on this side. This material is basically insulating when there is no light is falling. So, this is basically working like a capacitor. So, photosensitive layer behaves as a capacitor, right. Now, what happens is the deflection coils are so controlled that the electron beam scans the entire face of this. Behind the face plate, the pattern, if I look at the face plate now, the electron beam will start out somewhere, it will go through this, then it will return to towards the starting point and then again scan. So, it will keep on scanning horizontally and it will come back turned off. So, we are basically having patterns like this existing, basically horizontal lines, and so the charge is deposited, and when there is no light falling, you will basically it will equalize, the two charges will be equal, and it will no more electrons will flow because it cannot support any more charge. Sorry? I have not yet come to that. So I'm, this is basically when I'm looking from the front or from the back, then I'm seeing this portion here which is a rectangular plate. So this is the rectangular plate, and I have electron coming and striking at these points, meaning all throughout as is being scanned. If I use the horizontal deflection coils here, if I ramp up the voltage on these, then the electron is going to move with some uniform velocity across. It's actually the path of the electron would be that it will go further, then it will be slowed down, reversed in direction by changing the voltage, and then it will be electron beam will be turned off, it will come across, it will go beyond here and start accelerating. When it achieves uniform velocity, then it will start to, it will be this part of the scan. Yeah, it is if I look from the front here. This is looking from the side, this is the side view.
The electrons are coming from inside the tube to outside the tube.
They are not coming outside the tube, they are remaining inside the tube.
But how they are turning?
They are turning because of the magnetic field of the deflection coils. Alright, so we now have the photosensitive layer behaving like a capacitor. When the light falls on it, then the resistance of these globules changes. Resistance basically is proportional to 1 over the intensity. So if the light is intense, then resistance decreases a lot. These positive and negative charges equalize. Okay, there is a current flow that takes place here, and they neutralize the positive and negative charges. Next time when the beam comes to that particular spot, now there is a deficiency of electrons and that particular point, so the beam will deposit more electrons there. Okay, when that is done, there is basically a net flow of current that will take place from this electrode to the point where the beam is being generated. And if we look at this current, this will give us an indication of the intensity of light for any particular given instant of time, corresponding to that particular position on the image. So what we now get is, we basically get a current which is proportional to the intensity, and this is what we basically want. We can generate a pattern of analog values of this current and send it out as a video signal.
How the light is coming like this and then turning like this and being scanned like this?
Light is ending up here at this point.
The electrons, how the electrons
Yeah.
are coming from inside the tube to outside the tube, to the surface of the tube, and then they are turning 90 degrees and getting in this way.
It's not turning 90 degrees. Okay, let see. Basically, you have, okay, this is your face plate. Okay, this is the electron gun. So the electrons are injected into this, so they are going to strike here. Now the direction of the beam is being controlled, so instead of falling here, it will fall here and here. Then it will slow down, it will be turned off, it will come back here, and then again start and follow this. So the beam is moving in the direction perpendicular to the plane of the paper here.
I thought the beam, there were separate beams for each location.
No, the single beam, which is basically, if the deflection electronics is for that only. It basically scans through the entire area by horizontal lines, and each time is shifted down by a small amount. So you get a set of number of lines, and each line, the current flowing will give us the intensity corresponding to that particular point, right?
This actuation is being done by
The electronic deflection. Then you know the CRO and all that principle. It's basically similar. So there you are generating image. Here we are trying to capture the image. Okay. Now, so what I talked about was what we get. Now if I look at the face plate, So I have the beam traveling here, return part of the beam I'm showing as a dotted line, then it travels here again, returns, travels, okay, and finally it will come up here, it will travel here, last line, and then the vertical deflection control will take the beam, will turn it off, and will bring it to the beginning of the scanning pattern again. So this is the scanning pattern. Typically for US television signal, what they do is they use 525 lines, such lines they are done 525 times, out of which 480 contain image. Okay, rest are lost because of the blanking circuitry which is necessary for the beam to travel back, and so on and so forth. Now this whole exercise is done 30 times in a second. So you get, if I call each a frame, okay, one scanning pattern I am calling a frame, then there are 30 frames in a second. So if you do 30 times, then you get a more or less continuous type of visual effect for the TV viewing. Of course, there is a problem that by the time the beam comes back to the beginning again, the 1/30th of a second is elapsed and then something is moved. So there is a problem of flicker in this type of arrangement. So a slightly different arrangement is also used, in which instead of having a single pattern, what you do is, instead of having 525 lines, you will divide that by 2, you will have 262.5 lines, and you do that 60 times a second, so 60 FPS, and the pattern would be like this, that you will start out the beam here, then it will come back, then the next beam when comes back, okay. This is done, it will end up at this point, let us say it ends up here. Then instead of pushing it back here to the beginning, it will be pushed back half a line away. So then the scanning pattern will begin here, and return beam will bring it here, then scanning beam will be here. So we are basically filling up, you can say, the missing lines, and so the whole image is created once in these set of lines and other half line away from that. So that removes the flicker. So this is flicker free. Okay, and this is called interlaced image.
Why do I have to start again at the top?
Because well, you have to scan the whole area. One could do that, I am sure, but that is not done. Typically you have the electronics for bringing the beam back, turning the beam off at that time, and then taking it from the bottom to the top. So it is possible. I mean, if somebody wants to design a new camera, then you can start scanning backwards, upwards, and so on and so forth. Everything is possible, but these are the standards. Typically you would like, for digital images, you would like to have, instead of using 525 lines, one uses 559 lines, of which 512 belong to image, and this is useful because it is a power of 2, and storing the data, etc., becomes a little easier in digital images. One can have, this is 2 to the power 9 value, you can have 1024, or
What is the relation between these lines and pixels?
we will come to that. Okay, so now let us look at another technology that is used for image acquisition. In fact, that is what is more used, which is called CCD. This is charge coupled device. Okay, the basic structure is it is a solid state device. So, you have silicon substrate and basically use p type, on which you have insulating oxide layer, and then you form gate structures on this. And you have isolators. So, you have, so the basic idea is that if a light, you have photons coming to this gate and the gate is positively charged compared to the substrate. Okay, if gate, so this is first of all this is gate and this is gate isolation. Okay, these are photons. So, when gate is more positive, than substrate, then there is a potential well created. Okay, this leads to a potential well where electrons will get stored. Okay. So, electrons accumulate. Okay. So, what is basically done is that every other gate, you make a matrix of it, every other gate has a photodiode. So, when the light falls on that, electrons are generated, they get trapped in the potential well, and then the gate voltages are such manipulated that the charge or the electrons which are deposited there, which are stored there, gets transferred to the one which does not have the photosensitive part. So, it can be transferred from one side to another side by manipulating the voltages of these gates. Okay. Now, once that is done, so you can shift it out onto a shift register, and then the shift register you can manipulate and get a signal out from this. So, you can have both types. You CCD, you can have line scan cameras, and you have area scan cameras. Okay, line scan cameras are very common in let us say Xerox machines, where you have you look at one line at a time and then you scan through by moving the carriage, which basically scans the whole of the page. It is basically used for that type, either inspection type of systems or photocopying type of systems. Area scan is used for video images, and the area scan is basically you replicate the line scan technology in the other direction also. So, basic structure is something like this. You have photo site, which will be like for a line scan camera, you have these are photo sites, and then you have a gate structure which can be used to transfer the electrons from each of these photo sites by controlling the gate. So, we will call this the vertical gate. Okay. From the vertical gate you put it in a vertical this is transfer register. Okay. So, from this it can be transferred to that. Now, from this whole shift register you transfer it through another set of gates. So, these things are repeated here. What I have shown here is repeated along here, and each of these in turn will be, the voltages are again controlled so that they go through the horizontal gate into the horizontal shift register. Okay, so this will transfer at this one time, then next one will transfer. So in sequence they can be taken out from here through the output gate, and then suitable amplifier etc. will be there, and your video signal will be out here. So this is the basic technology. There is of course this very simplified way of showing it, but basically you generate photons, create electron accumulation, and that whatever electrons are accumulated depends on the intensity of the image at that particular point. Then these are sequentially transferred by using proper electronics of the gates to shift registers, where they are sequentially transferred. All the vertical ones are transferred out to the horizontal ones one after another until you have a composite video signal.
Only the charge at one photosite is selected.
Yeah. So each of them are sequentially put and you generate the signal. So it's basically analog signal in both of these cases. Okay. So typically it will look like whatever, depending on the image, and then you will have after each frame there is some blanking time, and then the whole thing repeats, and this has to be interpreted with each of these representing a line, and then it will have to be, if you want to generate a image frame or a digital image matrix, then one will have to sample these and take out digital values and store them away. Okay, that is the task of what is called a frame grabber card. Okay. So typically you have the resolution used to be low in these cameras, but nowadays you can get pretty good resolution even in CCD. Earlier VDCon was preferred because you could get resolutions of thousands of pixels, whereas CCDs were restricted to 32 by 32 matrix or 64 by 64 matrix, at most maybe 256 by 256. But nowadays you can get easily 1024 by 1024 type of image from CCD. Okay, let's move on now and let's see what the image then is. Okay, essentially now you have from the composite signal, which is audio signal, sorry, analog signal, you are going to sample it video signal, okay, at some rate using the frame grabber card. So each of the scan line obviously is discretized because you have only so many discrete lines. On each of the line, the analog voltage which is there is going to be sampled, and that will give rise to discrete digital values depending on the accuracy of the conversion process. So you require A to D conversion, right, and then so you have then spatial discretization. Okay, first of all, due to discrete lines of the scan, and due to sampling time of A to D converter. Okay, you also have discretization in the intensity values, in grayness or brightness, whatever you want to call it. Okay, this is due to finite number bits of digital value. Okay. So now once you convert this into a digital thing, so you have basically divided your, if this is my x and this is my y, then I have divided my x and y's into discrete intervals, and each of these little squares will be having some intensity value, and that intensity value, let us say x y, where it is x distance away here and y distance away here. Okay. So this is basically called a picture element or a pixel. Okay, picture element is called a pixel for short. Now this pixel, depending on the kind of image that you have, you can, if you have a color image, then it will have maybe several bytes of information. If you think of RGB as 3 separate bytes, each having 0 to 255 intensity values, then you can make so many million colors. Okay, or if that is too much memory, then you could restrict yourself to gray levels image, which will be 1 byte per pixel. Or if your information is only that you require whether part is there or not there, you could deal with a binary image. A binary image has pixels which are either 1 or 0 binary value, black or white. So that is depending on what levels of gray you have, you will have different looking pictures for that. This is the discretization and brightness, which is represented by this function fxy. Okay, then we will look at lighting, which is very important part of image acquisition. Okay, unless you have proper lighting for the image will come out to be poor quality, then it becomes very difficult to process it. So typically you use different type of lightings. One is diffuse lighting. Okay, in diffuse light, if you have some object, let's say it's with some continuous curves and all that. So if I have an object, then I diffuse the light. So I don't use a light source directly. I may have a ground glass here, and then I have light sources behind it, so that what I get here is a diffuse light. Then I will see continuous change in intensity because of the surface features or surface curve which is existing here, and that will be useful for looking at objects like that when we want detail of the overall surface or the curves of the surface. Another useful type of lighting is what is called backlighting. Okay, in backlight you will put, let's say you have source of light here underneath, and then you have a ground glass semi-transparent type of thing, and then you have a part lying here, whatever the part may be looking like. So if I look at from the top now, I will see a silhouette. Okay, which means wherever the object is there, I will see darkness, and wherever the object is not there, I'll see bright. So it directly gives me a binary image. The advantage of the binary image obviously is that you don't have to deal with so much information. The processing of the information becomes faster, but then you lose features which are there on the surface. You have either bright, I mean 1 or a 0 there. So that is only limitation that you have. If you are only looking at the contours of the outside of the shape, and that is sufficient for you to know what the object is like. If you're dealing with basically flat objects of different types, then this will be a good technique to use. Okay, there is one type of lighting called structured lighting. Okay, in this what is done is, instead of having a general diffuse light, you have patterns of light which are generated. For example, if I have a sheet of light, now I am looking from one side, I have a sheet of light which is going into the paper, and there is another sheet of light, both of them coming at one line basically. So, if this is my surface here, and if I have a camera looking down here, then the image that I will see will, if this is the image that I am representing which is seen in the camera, you will see a bright light here. Okay. Now, supposing we have an object which is, this may be a conveyor belt, and then the object is moving and it comes and hits one of the lights. Okay. Immediately what will happen is, you will see that depending on the width of the object, so if the object is only partly wide, you will see another light which will be corresponding to the reflection of the light beam from this point of the object. So, you have this beam which is being reflected and seen as one big line here across, and then you have a smaller line which is seen as the width of the object is the length of this line, and it is displaced from there, because now it is hitting at a different point. So, if I wanted to detect an object in such conditions, then it will be very easy to detect, it will be easy to process this particular information, and therefore structured lighting is very useful for simplifying the task of image processing, which we will see is not so trivial. Okay, there can be different structured lights. This is just one example I have shown. You can have parallel sets of planes of light which will give you a stripe pattern on the surface of the object, and then you can discern the shape, orientation of the objects by looking at what kind of pattern is resulting. Lastly, I would say that you can have directional light. And this is basically, if you have if this is my object or surface that I am looking at, I can have light falling at a very oblique angle. So, what happens is all the features, the surface features of the object gets highlighted. You will have micro shadows falling for the little ridges which may be there, and whatever features are there. So, you can discern texture using this type of light. Okay. So, depending on the lighting, you will get different type of image, and it is very important to have the correct type of light for a given situation using image processing. Okay, having basically seen how the sensing part is done using a VDCon camera or a CCD camera, I would like to contrast this now with human vision, so that I would like to bring out the issues to you, what is important in terms of actually processing the images. So, if I look at the human eye, basically you have front portion which is the cornea, okay, this, and then you have basically the eye which is spherical in shape, with different layers inside the eyeball. You have the retina which is the sensitive part, and you have all these things between the retina, this is the retina, okay, and between the retina and the what is called the sclera, you have another layer which carries the blood to the eye and supplies it with the blood that is necessary to keep these cells alive. And then you have iris and the lens, and the lens is supported on fibers here which are basically muscular, and also the retina is connected to muscles here which are called ciliar muscles. Okay. This spot here is very, very important, which is called fovea, and you have the optic nerve going to the brain. Okay. The optical axis passes through the center of the lens and onto the fovea. Now, human eye is remarkable. You know, this is, you have basically a diameter of 2 centimeters, and the number of sensitive parts on the retina, including the fovea, are in millions and millions. Okay. So, we are talking about sensitivity of the camera. If you think about an image of 1000 by 1000, right, you have 1 million pixel elements, and if you have to do this let us say 30 times a second as the frame rate, then you know that you have 1 over 30 millionth of a second available to process each of the pixel. Process meaning there is an analog value, there is an analog signal which has to be converted into a digital value. So, that is the A to D conversion, the analog to digital conversion has to take place in 1 over 30 millionth of a second, and that is what basically you can see the number of pixels that we can deal with gets severely limited by that. How much, because the amount of information that is there is truly remarkable. If you look at the human eye, you have 6 to 7 million cone, what is called cone receptors. These are primarily limited in the area of the fovea. Okay, fovea itself is carrying something like 5 million cone receptors. Each of these receptors is individually connected to a end of a nerve. Okay, so you have all these millions of connections, and these are good for bright light vision. So, the remark is it is fantastic kind of a resolution that we are talking about, and this is only a area which is less than a centimeter, much less than a centimeter, few millimeters in size. So, the way we look at things is that we whatever we want to see, we bring it to this particular fovea by rotating the eyeball, and bringing whatever we are interested in into the center part, the fovea part, so that we can discern the details there. Out here we have some cones, but we have mostly what is called rod receptors. Okay, in most of retina. And there are something like 75 to 150 million rod receptors. So, that is much larger than any camera receptor. These are not good for color vision. They basically work with dim light, okay, and they give basically a gray type of image.
So, what we are seeing in front is the green fever cone receptors is what right now I'm seeing at the sideways blur images.
Well,
are those the rod receptors?
No, there are some cone receptors, but there are no rod receptors in the fovea region.
So, like right now when I am focusing towards front side, I can have an idea about what's happening here also.
Idea, that is the key word. It is the image which is constructed in your brain, is not necessarily what you are seeing. Because I know Avinash is sitting here, I am looking at that person, I see a red shirt there, I do not see his face clearly at all, but I know it is Avinash, right. So, that is the key. In human image processing, the processes are very complex. You have the whole experience, you have your memory which aids you.
But that's a processing step. Like you are having some images from here also, some idea, like you are seeing receiving some light from here also.
Yeah.
So are those being interpreted by the cone receptors or the rod receptors?
In the daylight, there will be, when the light is sufficient, it will be mostly cone receptors.
Which without
So
thinking
if you
about
see
it.
even in daytime you look at a picture which is bright and colorful, you can see it.
No, so like
If you put
that's
that
what
in
we
moonlight,
that's what we focus on. Like the things which we on sideways. So I see something on my rod receptors and then I turn my head
yeah,
to bring that in my focus of full receptors.
then you will see the details of what is happening at that particular point at the instant, right? But the image doesn't vanish away. Even if I close my eye for a moment, I can continue to see what I was seeing earlier. So the brain keeps the image alive. Okay, of course that can also be used to fool the brain. Okay, so you can have various optical illusions and so on and so forth, which are basically reflecting in the complexity of the way the brain interprets what is seen by the eye. So sometimes what is not there, you will start seeing it because of the way the brain functions, right? But by and large it helps us to see huge amount of detail without as much processing as you will imagine will be required with these kind of number of pixel elements, talking in terms of hundreds of millions of pixels, and we are doing all the time real time. We look at one glance and we know, we immediately have interpreted what is there. Okay, that's why the danger is that we do not appreciate what is required in machine vision until you start to do things yourself and try to interpret and try to even determine simple type of things, that whether such and such part is present or not, or where it is present. Then you run into a huge problem because it's not easy. Okay, and that is, it's not easy and it feels easy because we are so used to it. Because if you imagine that you basically have a matrix of numbers, right? So you have intensity level at this particular pixel, you have intensity level at this particular pixel, and so on and so forth. Supposing I have m pixels along this direction, then you have some other intensity here, and so on and so forth. If I have n pixels in this direction, then I have so many intensities are involved here, right? This is basically my image frame, digital image frame. Now each of these is a number. Finally, how do I know that there is actually a block sitting here? Right, this picture is, finally it boils down to, in the computer, a set of numbers in a matrix like this. They may be values from 0 to 255, they may be values, 3 values from 0 to 255, or they may be a single value 0 or 1, okay, a bit of information, whatever it is. Finally these are representing some things in the real world. Then that is why all these steps are required, that you need to enhance the image, you need to remove the noise, so that we are looking at basically what should be represented for the outside world. Then we are later on trying to segment the image to see, okay, this part is different than the rest of it here, around here, okay, or something here is different than the surroundings. So we will segment it into different regions. Then we will try to say, okay, this region must be something, or what kind of region is it? If you have color information, then color provides a useful set of information that you can many times distinguish this blue sheet from the white surroundings because the property blue. Okay, so that is the description part, that we describe a particular region with some attributes. It may be color, it may be size, it may be shape, it may be variety of things. It could be like, how do we distinguish a letter from an object or a alphabet from an object, because we look at text. Then we will use some properties which are going to distinguish it from other objects. So once we haven't done that, after that we will try to recognize and say, okay, this is part of the top of the box because this is green in color, okay, this is the side of the box because it's red in color. These are simple ways of doing it, but when you don't have such clear cut color information available, then things are, you have to determine based on the intensity values. and not only intensity values, how the intensity values are changing suddenly. So if you have an object here which is, and you have a light source, so this face is bright, but here you have a shadow coming which will of course look like a different region, okay, but there is no object corresponding to that, it is only the shadow of the object. So we have to distinguish it away, we have to not use that, we have to recognize that as a shadow, and so on and so forth. So the task is not very straightforward, is what I am trying to point out. And we will appreciate that as we go along and look at different parts or tasks involved in image processing, which will be required for the robot to use that information in some sensible way. Typical way the robot will be required to use the vision information is that you have a scene in which you may have number of objects coming, you may have nuts coming, bolts coming, washers coming on a conveyor belt in some random order. Then we have only a few of these given objects and we have to identify which is which, so which is one type of task, and then having identified it in the right order, the robot can take the gripper to that particular location, pick it up and use it in the assembly, let us say. The other type of tasks will be robot is required to do some continuous path motion, say in spray painting could be the one, but spray painting you usually do not use vision, you will use vision in say welding application. So your seam tracking, you want to know where the seam is so that you could move the torch or the electrode for welding along that particular seam. Then you would like to use vision to see how the weld pool looks. Am I moving too fast? Am I moving too slow? Is the temperature too high, too low? All these kind of information you would like to derive from a vision based system. Or you may have tried to duplicate what human beings do. You may have a bin full of parts in different random orientations and you have a robot with a vision system. You want to say, okay, this particular part is lying in this orientation, this is on the top of the bin, right? I want to know both this information so that I could go and pick it up. So the variety of tasks, basically vision will possibly give capability to the robot to duplicate some of the tasks which humans do quite easily. So we will stop here